Welcome back to another die-hard American metal explainer. Today, we're talking about something you can't see, but it's the difference between running at max speed and just making a giant pile of scrap. We're talking about the feed curve.
Really think about it for a second. You've got this massive multi-ton press just slamming down hundreds of times every minute. And in that tiny fraction of a second when the die is open, your feeder has to whip material into place with micron-level accuracy. How on earth is that even possible? How do you get that perfect dance between blinding speed and insane precision without the whole thing just shaking itself to pieces?
Well, the secret isn't just throwing a bigger, beefier servo motor at the problem. Nope. Brute force alone, that'll just get you nowhere fast. The real magic, the secret sauce that tames all that chaos, is actually a super sophisticated digital blueprint, a set of instructions that controls every single nanosecond of that feed.
And that's what we call the feed curve out on the shop floor. But technically, it's a motion profile. It's the pre-calculated set of commands that tells the motor exactly how fast to go, how hard to push, and precisely when to stop. It's the brain that guides all that brawn, you know? It turns that raw horsepower into repeatable, pinpoint precision.
All right, so let's get into the weeds here. To really wrap your head around the feed curve, we've got to break a single feed cycle down into its 4 basic parts. Seriously, every single move your feeder makes, it follows this exact same sequence.
The easiest way to think about it is like a drag race, right? First up, you've got accelerate. That's the launch. You're flooring it, getting off the line as fast as you can. Then you hit slew. That's when you're at top speed, just flying down the track. Next, you've got decelerate. You got to hit the brakes with perfect timing to stop right on that finish line, not an inch past. And finally, there's dwell. That's the pause, the time your crew has to get their work done before the next race starts.
Now listen up, because this dwell phase, it is absolutely critical. It's not just downtime, it's not idle time, it is money time. This is the actual window where your press is making a part. Stamping, forming, punching, you name it. And if your feed curve is slow or inefficient, it just eats away at this precious window. A bad curve can shrink your dwell time down to almost 0, and that forces you to either slow down the whole press, or even worse, risk crashing your very expensive tools.
So you can see that how the machine gets through those first 3 phases, the acceleration, the slew, and the deceleration, well, that changes everything. And that brings us to the 2 main approaches, the 2 big philosophies when it comes to motion control, and believe me, they are very different.
Okay, on one side you've got the trapezoidal profile. We're going to call this one the hammer. It's all about brute force, raw power, maximum speed. It just hits hard and fast. Then on the other side you have the S-curve profile, and we'll call this one the scalpel. This one is all about smooth, controlled, precise movements. It's elegant, it's graceful.
So, what's the big difference between the hammer and the scalpel? Well, it all boils down to one super important engineering concept: jerk. Yeah, I know, funny name, but think about it like this. When you're in an elevator, you don't really feel the speed, do you? What you feel is that jolt when it starts and stops. That jolt, that is jerk. It's that sudden change in acceleration that slams you against the wall or makes your stomach feel like it's in your throat.
And this quote right here, it gets to the very heart of why jerk is basically the villain in our story of high-speed feeding. That jolt, it's not just a feeling. It is a destructive force ripping through your press line. The hammer's high jerk sends a shockwave through everything: the gears, the bearings, the material itself. It's the #1 cause of vibration, it chews up your expensive components, and you guessed it, it's the main reason your material slips in the rolls.
Okay, take a look at this table. It makes the trade-off crystal clear. If you look at that first row, cycle time, yeah, on paper, the hammer, the trapezoid, it looks faster. But just follow that column down. The cost for that speed is infinite jerk. That leads to high vibration, a ton of mechanical stress, and a huge risk of material slippage. Now look at the scalpel. It might be a fraction of a second slower in theory, but it wins on every single other metric, all the ones that actually affect your part quality and the health of your machine.
And listen, this isn't just academic theory, okay? Choosing the wrong profile or even just setting it up incorrectly has real, tangible, and oh-so-expensive consequences out on the shop floor. So let's take a look at what actually happens when the math doesn't line up with the mechanics.
This right here, this is one of the absolute worst things that can happen in a progressive die. Let's say your feed profile is just too slow for the speed you're running the press. So, as the RAM is coming down, The feeder is still pushing the material forward, at the exact same instant that the pilot pins are trying to engage the strip to locate it. It becomes a literal fight between the feeder and the pins. And let me tell you, the loser in that fight is always your incredibly expensive tooling.
And the results are, well, they're ugly and they're immediate. You get bent pilot pins, you get elongated pilot holes, and just like that, every single part you're making is scrap. Your die is now at risk, and you're looking at a massive repair bill and hours, maybe even days of downtime to fix a tool that you just crashed.
So what's the cause? It's really just a simple timing conflict. The feed isn't finished before the pilots are trying to do their job. The solution then is to get them back in sync. You've got a few options. You can slow the press down to give the feed more time. You can tell the controller it has a bigger feed window to work with, assuming the die allows for that. Or you can make the feed curve a bit more aggressive so it finishes the job faster.
Okay, here's another one that drives operators absolutely nuts. The feeder is just constantly faulting out. You're getting over-torque or over-current alarms, and it stops the entire line. So you clear it, you restart it, and a few minutes later, bam, it happens again.
This is a classic hammer problem. You're basically telling the motor to accelerate this huge, heavy coil of steel from 0 to 60 in a ridiculously short amount of time. The motor tries its best, it draws a massive amount of current, and the drive, to protect itself, just shuts everything down. The solution here isn't more power, it's more intelligence. By switching over to an S-curve, the scalpel, you apply that force much more gradually. You let the motor get all that mass moving without causing that huge fault-inducing current spike. Okay, so understanding the theory behind all this, that's half the battle. The other half, the really important part, is implementing it correctly out on the floor. Mastering your motion profile is all about turning this knowledge into higher speeds, better parts, and a whole lot less downtime.
So how do we get it right? Here's the game plan. First things first, it all starts with the fundamentals. Remember, electronics can't fix bad mechanics, so perfect mechanical alignment is absolutely non-negotiable. From there, it's all about intelligent setup. Use the tools in your controller, like a feed advisor, to get a good baseline. Choose the right profile for the material you're running. And then you've got to fine-tune those critical settings, like your roll pressure and your pilot release timing.
So what's the bottom line here? The choice between the hammer and the scalpel. It's not just some random setting you pick on a screen. It's a real, deliberate engineering decision, one that directly impacts your speed, your part quality, and, yeah, your bottom line. The good news is, you now have the knowledge to make that choice intelligently. The feed curve puts you in command, so the only question left is, what are you going to choose for your next job? Brute speed or ultimate control?